With the incredible capabilities of massive machine learning models, especially these foundation models, it's easy to just marvel at what they can do.
Absolutely.
But trying to understand how each individual piece of training data actually contributes to that final output, that's been a real puzzle.
A huge one, like, trying to figure out which drop of rain raised the river level.
Exactly. But it seems there's a fascinating new approach emerging, one that offers some surprisingly clear answers, and it does it really efficiently, too.
Yes, that's what we're diving into today. It's called in-run data Shapley. It's a genuinely novel technique for figuring out data contribution during a single training run of a model.
Okay, in-run. So let's unpack this. Why is figuring out the contribution of individual data points such a big deal anyway? I mean, if the model works well, isn't that what matters most?
Well, understanding the contribution unlocks a lot. Think about it, if you know which data is most influential, maybe you can train faster by focusing on it.
Ah, okay. Like prioritizing the best stuff.
Exactly. Or for cleaning up data sets, finding and maybe removing data that's problematic or just not very useful.
Right.
And, especially with generative AI now, it gets into really fundamental questions about, say, copyright or where the model's knowledge actually comes from.
Okay. So it's not just academic curiosity. There are real practical reasons improving efficiency, data curation, even legal stuff.
Definitely. It's about getting a much deeper insight into why a model works the way it does.
And this new method, in-run data Shapley, you're saying it's a significant leap forward compared to what we had
A
before.
really big leap. The traditional ways to measure data value were just incredibly computationally heavy.
How so?
They often involve retraining the model over and over again on lots of different subsets of the data.
Right, I've heard about that. Sounds slow.
Extremely slow. And for the kinds of massive models we have now, foundation models, it's basically impossible, just completely impractical from a resource point of view.
So in-run data Shapley avoids all that retraining.
That's the core idea. It offers a huge improvement in efficiency, making this kind of data attribution actually feasible, even for these giant models. It's much more targeted, much more resource friendly.
That is exciting. So the mission for us today in this deep dive is to really get under the hood of in-run data Shapley. We want to focus on the innovative ideas that make it so efficient and what this means for understanding how models actually learn. This is a real advancement, academically speaking, right?
Precisely. We're basing this discussion on the research paper Data Shapley in one training run. And we really want to highlight how this work introduces a truly innovative solution to a pretty old and important problem.
Okay, great. Let's start with the old way then. What were the main limitations of traditional data Shapley? You mentioned the computational cost, but what else?
So the basic idea of Data Shapley is solid, assign a value to each data point based on how much it helps the model's final performance. It comes from game theory, actually, the Shapley value, trying to be fair about distributing the credit.
Okay.
The standard method, retraining-based Data Shapley, estimates these values by, like we said, training and testing on tons of different data subsets, seeing what happens when you include or exclude a specific point.
Which, as you said, is computationally brutal.
Exactly, it scales terribly. For the huge data sets behind foundation models, billions, even trillions of points, retraining on all or even many of the possible subsets, it's just astronomical. You can't do it.
So, besides the sheer cost, were there other, maybe more conceptual problems with that retraining approach, especially if you want to understand one specific model you just trained?
Yes, definitely. Two big ones, really. First, because you're averaging across many different training runs on those different subsets, the values you get can be a bit unstable, especially if your training process has some randomness, which it usually does.
Ah, so the noise in training can affect the scores you get.
Right. Stochastic algorithms introduce variability. But second, and this is maybe more important from like an academic or theoretical standpoint, retraining doesn't really tell you the contribution of the specific model you ended up with after one training run.
Explain that a bit more.
It tells you the average contribution of that data point to the learning algorithm in general, averaged over many possible outcomes. But if you've trained one specific model instance, say your final production model, you want to know what data influenced that exact model. Retraining doesn't quite give you that.
Gotcha. That makes perfect sense. You train one model one time and you want to know what shaped it. Okay, so this leads us right to the innovation. In Run Data Shapley, how does this new paradigm fix these issues?
Well, the core innovation, the big idea, is that in-run data Shapley quantifies the contribution of each data source to a specific target model that you get from a single training run.
Okay.
And it does this valuation within that same training run. No need for all those extra retrainings afterwards.
In Run, okay, so it's baked right into the training loop somehow. How does it manage to figure out the contribution on the fly like that?
It uses a really clever divide and conquer approach. Instead of trying to assess the value over the whole training process at once, It breaks it down. It looks at the contribution iteration by iteration.
So at each single step where the model updates its weights.
Exactly. It calculates a kind of local value for each step.
How's that defined?
So for a single iteration, let's call it T, and using a specific batch of data S, it defines a local utility. Think of it as measuring how much the loss changes on a separate validation example after that one update using batch S.
Okay, so it checks the immediate impact of that training step on how well the model performs on some validation data.
Precisely. It's U dollar, the loss after the update minus the loss before on that validation point Xi.
Right. So how does that local step-by-step impact relate to the overall contribution of a data point across the whole training?
Well, the global utility for a data subset S over the whole run is just the sum of all those local utilities. It represents the total cumulative change in validation loss.
So it adds up the effect over the entire training journey.
Exactly. And here's the really neat mathematical part, the key insight that makes this efficient. Shapley values have a property called linearity,
Okay.
which means the overall Shapley value for the global utility is just the sum of the Shapley values of all the local per iteration utilities.
So you can calculate the value for each tiny step and just add them up to get the total value for a data point.
Precisely. This decomposition is what makes it tractable. It breaks down this massive problem into manageable pieces. And importantly, it satisfies the efficiency axiom: the sum of all the individual data point values equals the total improvement in validation loss over the training.
That's very elegant. It avoids the need for retraining by breaking it down iteratively. But how do you actually calculate those per iteration Shapley values efficiently inside the training run? That still sounds computationally tricky.
Yeah, you're right. That's the other half of the innovation. The conceptual breakdown is great, but making it work fast in practice is crucial. And the key here is using approximations, specifically Taylor series approximations.
Okay, Taylor series, like approximating a curve with a line or maybe a parabola locally.
Exactly that idea. Since the change in the model's weights during a single training step is usually small, a first order linear or second order quadratic, Taylor approximation of that local utility function works really well.
And how does that help with the efficiency?
Because the Shapley values for these approximations can be worked out analytically. You get formulas for them.
Formulas involving what?
Gradients, mainly. For the first order approximation, the Shapley value for a data point Z at iteration T ends up being proportional to a dot product.
A dot product. Between which vectors?
Between the gradient of a loss calculated on the validation data point and the gradient of the loss calculated on the training data point Z. Both gradients taken at the current model weights with dollars.
Okay, wait. Gradient dot product. So it's measuring how aligned the direction the training point wants to push the weights is with the direction that actually helps performance on the validation set.
Exactly. A big positive dot product means the training point is pushing the model in a helpful direction for generalization, at least according to that validation point.
That makes intuitive sense. And the second order approximation.
The second order one adds another term. This one involves the Hessian matrix, the matrix of second derivatives of the loss.
The Hessian captures curvature, right? How the gradients are changing.
Right. This second order term essentially accounts for the interaction between the training point Z and the other points in the same training batch. It considers the curvature of the loss landscape.
Why is that interaction important?
Well, imagine you have two very similar redundant data points in a batch. The second order term can help recognize that redundancy. It might reduce the individual value assigned to each of them, giving a better picture of their unique contribution.
I see. So first order is about direct alignment. Second order refines that by looking at interactions and redundancy within the batch using the loss curvature. Okay, so Taylor series give analytical formulas using gradients and Hessians. But computing per sample gradients, and especially anything involving the Hessian, can still be really expensive, right? How do they get around that?
This is where the really clever implementation tricks come in, the ghost techniques. This is a major part of the computational innovation.
Ghost techniques? Sounds intriguing.
They developed methods to calculate those necessary gradient dot products and even the terms involving the Hessian very efficiently. They can do it using just one or two backward passes through the network.
Without actually calculating and storing every single gradient for every example. Or the giant Hessian matrix.
Exactly. They avoid forming those explicitly, which saves a massive amount of computation in memory.
How do these ghost things work, roughly?
Well, for the first order value, the ghost dot product uses the chain rule during the backward pass in a smart way. It calculates the bits needed for the dot product essentially for free, alongside the normal gradient calculation for the weight updates.
Wow, okay.
For the second order value, which needs that gradient Hessian gradient product, they use a similar idea, but it typically requires one or two extra backward passes with specially constructed ghost vectors. But crucially, it still avoids computing the full Hessian. These are really neat algorithmic tricks.
That sounds like a serious technical achievement. So what does this mean for the actual runtime? How much slower is training with this print-on?
The results are pretty amazing. The first order in-run data Shapley adds almost negligible overhead in their optimized implementation. It's very close to the standard training time.
Negligible, seriously.
Yeah, if you have enough GPU memory. The second order version is slower, roughly doubling the training time. But even that is way, way faster. Like, they report over 30 times faster than a naive approach that would calculate all the per sample gradients explicitly.
That's incredible, negligible extra cost for the first order version to get these kinds of insights. That really does make it practical for huge models. That's the game changer.
Absolutely. That efficiency is key to its practical value and a core part of the innovation here.
Okay, so we have first order and second order. Let's clarify the difference and what they tell you again.
Sure. The first order approximation, that formula with the gradient dot product, scale back the rotor error of the quadratic and $dollars on the board of $1, scaled by the learning rate etod across all training steps. It captures that direct relevance.
And you mentioned this connects to another method.
Yes, interestingly, this first order calculation turns out to be equivalent to a method called trace and ideal that was proposed earlier. So in-run data Shapley provides a nice principled justification for trace-in based on Shapley values.
Okay. And the second order adds?
It adds that gradient Hessian gradient term. This brings in the context of the rest of the batch and the curvature. It helps understand not just if a point is relevant, but also how unique its contribution is compared to others nearby in the loss landscape.
So if that second order term is large, what does it signify?
It suggests there's a strong interaction effect. For example, if a point is very similar to others in the batch, redundant, this term might counteract the first order term, reducing its overall value. It gives a more nuanced measure, considering both relevance and uniqueness.
Got it. First order, direct impact. Second order, impact considering context and uniqueness. Now, for listeners who really want to dig into the weeds, you mentioned the paper has appendices on these ghost techniques.
That's right. Appendix D type 1 goes into the ghost dot product for the first order calculation, showing the chain rule math and the equations involved. D.2 tackles the ghost vector Hessian vector product for the second order, explaining how they compute it efficiently with those extra backpropagation passes. They also mention practical things like gradient accumulation for saving memory if your batches are huge.
Good to know for the technically minded. Okay, let's talk about validation. How did they test this out? What did the experiments show?
They ran experiments using a GPT-2 small model. The data was from the pile data set, specifically the parts that aren't copyrighted, which is important. This is a pretty standard setup for research on large language models.
And what did they test?
They looked at a few things. First, runtime, obviously, to confirm the efficiency claims we just discussed.
Which checked out, especially for first order.
Exactly. Then they did a case study applying it to GPT-2, comparing it against other methods like influence functions. They also looked at how the values of different data sources changed during the training process, which is super interesting. And finally, they tried using the Shapley values for data curation, basically, filtering the training data.
Okay, lots of angles. What were the key findings, especially the ones highlighting the innovation?
Well, the runtime results, as we said, were a big validation of the ghost technique's efficiency. That negligible overhead is a key innovation for practicality. In the attribution case study, in-run data Shapley, especially the second order one, did a better job than influence functions at identifying which parts of the training data were most relevant for specific knowledge, like math problems from the RCF corpus.
So it's better at pinpointing relevant data sources?
It seemed to be yet in their experiments. They used a metric called normalized recall at 1,000 for that. Then looking at how values change over time was fascinating.
What did they see there?
For example, data from RCF, academic papers, became more valuable later in training when the validation set was math-focused. Makes sense, right? The model learns basics first, then specifics.
Yeah, that tracks.
But even more interesting was the PileCC corpus general web crawl data. Its value was high initially, suggesting it helped learn basic language structure, but then its value actually dropped, sometimes even becoming negative later on.
Negative. So it started hurting performance.
Potentially, or just became redundant once the basics were learned. This temporal view gives a much more nuanced picture than just a single value at the end. That's a novel insight enabled by the in-run nature of the calculation.
That is really interesting, seeing the value evolved and the data curation experiment.
That showed a direct practical benefit. They tried removing corpora that consistently had negative Shapley values throughout training. And the model trained significantly faster. It reached the target loss level using about 25% fewer training iterations.
Wow, a 25% speed up just by filtering based on these values?
Yeah, roughly. And perhaps surprisingly, they found about 16% of the corpora in the pile, even though it's considered a curated data set, had negative values overall.
16%. That's quite a lot. It suggests even good data sets might have chunks that aren't helpful or even detrimental.
Exactly. It really underscores the potential utility of this method for improving data quality and training efficiency, even on supposedly clean data sets.
These results really seem to back up the method's value. Did the paper mention any limitations or areas for future work?
Yes, they were upfront about a few things. One is needing that validation data available during the training run itself. They suggest maybe using checkpoints if you want to evaluate against validation data chosen after training, but it's a consideration.
Okay, what else?
Another point is the current focus on the SGD optimizer. Adapting these efficient ghost techniques to optimizers like Atom, which have extra normalization terms and momentum, isn't straightforward. That's an area for future research. They used SGD as a reasonable proxy in their work.
Right, Atom is very common, so extending it would be valuable. Anything else?
They also briefly mentioned memory. While the ghost techniques save computation, you still might need strategies like gradient accumulation if you're using extremely large batch sizes just because of the memory footprint of activations and gradients.
Standard large model training challenges then. Okay, so summing up, what are the biggest takeaways here? What are the core implications and the real innovative breakthroughs of in-run data Shapley?
I think the biggest thing is providing a way to understand data contribution that is both computationally feasible for large models and targeted to a specific model from a single run. That combination was missing before.
Addressing those key limitations of retraining methods.
Exactly. The analytical approach using Taylor series, and critically, the ghost techniques enabling efficient computation, those are major academic and practical advances. And the potential applications really understanding data for copyright questions, better data curation for pre-training, making training more efficient, these could have a significant impact on how we develop AI.
So the core innovation, a scalable, targeted method within one run made possible by those efficient computational tricks.
That's the heart of it. It opens the door to a much deeper, more actionable understanding of the data that powers these complex models.
Okay, learner, I hope this deep dive has really shed some light on in-run data Shapley for you. It's a really cool example of how theoretical progress can lead to practical tools with potentially big consequences.
And it really highlights the push in the field, not just to build bigger models, but to actually understand how they learn from the data we feed them.
Absolutely. So here's a final thought for you to chew on. Now that we have techniques like in-run data Shapley, offering this fine-grained view of data value, how might this fundamentally change how we approach data in AI? From the way we collect it to how we clean it, maybe even how we think about the ethics and ownership of the information used in training.
It's definitely something to think about. This discussion gives you the foundation. If you want to go deeper, we definitely recommend checking out the original paper, Data Shapley in One Training Run, and the related work in this area. It's a fast-moving field with lots of interesting developments.